So in this video, we will be deriving the heat diffusion equation for Cartesian coordinates. So as you can see, I have a diagram here where we have the heat flow going into this side here and then coming out with the change in x. So how we're going to derive this equation is we are going to start out with an energy balance where we will have the energy in minus the energy out plus the energy generated, and all that will be equal to the energy that is stored. So again, let me just write this down up here. We will have the energy going in minus the energy going out plus the energy that is generated, and all that will equal the amount of energy that is stored. So now we can start plugging into this equation that we have written down. So obviously our En is just going to be our heat flow here, Qx, and then minus our energy out. And as you can see right here, we have this Qx plus dx, our change in position. But we also need to take into account that our heat flow could be going through at different rates. There could be a reaction in here, or depending on what type of material it is. So we need to have some way to account for that. And how we're going to do that is, again, we'll have our heat flow coming out, but then we will have a partial derivative of our heat flow with respect to position, and then still multiplied by our change in position. And then EG and EST will stay the same. So now we can look at energy generated. And that is going to end up being a flow. So we're going to call it energy generated, EG, with a dot on top because it is a flow. And it will be equal to the flow rate, Q, that's density, rho, Q, and that will be in joules over seconds, meters cubed, and then times the differential area, dV. And what dV is dV is just all the differential areas of the different axes multiplied together. So dx, dy, and dz. So if we look over here, we already have dx here. This will be dy, and then dz down here. So now we can look at the energy stored, EST. And that is going to be equal to the density rho times the heat capacity, CV, times the partial derivative of the temperature over time, and then multiplied by the differential area as well. And this part right here is going to be very important because it will be telling us how the energy stored will be changing based on the change in temperature over time. So, as you can see, the temperature will be changing as the flow comes in from this side and exits here. So it will be changing throughout the area of this cube, not linearly. So now what we can do is we can plug this all back into this equation up here. So the first thing that we notice is that these can cancel, and then we can distribute this negative out over here. So it'll end up being negative partial derivative 2x over partial derivative x dx plus then our energy generated equation q dv, and then that will be equal to our energy stored equation rho cv partial derivative t, and again that's temperature, and the bottom is time, and then differential area dv. So now I'm going to just copy this up here. Because now what we can do is we can find something to plug in for this heat flow right here. And how we're going to do that is going to be Fourier's law. So let me finish copying this down. dv rho cv So now what can we plug in for our heat flow in this equation? So what we're going to be using is Fourier's law, which is going to be that heat flow Qx is equal to the heat flux times the area and then we can simplify that more by rewriting this as the negative of the heating thermal coefficient times the partial derivative of the temperature over the partial derivative of x times dy dz. So now we can plug this in up here for our heat flow, and we will end up getting negative k times partial derivative of the temperature squared over the partial derivative of x squared dz, dv, and then all this will stay the same. And then now, as you can see, these dv's will cancel. And now we can also divide everything by k to get rid of this. So then we will end up having negative partial derivative squared the temperature over partial derivative squared of x plus q over k, and then rho CV over k times our partial derivative of the temperature over time. So I did notice a little mistake here. There should be heat capacity at constant pressure, CP. I think I messed it up when I was copying down up here. There should be CP here, not CB. So now the final thing we can do here is we can actually simplify this part right here. And how we can do that is we know that the thermal diffusivity is equal to K over rho CP. So then that will just be the inverse of that. Sorry, not negative, the inverse, 1 over. So we can plug that in here and keep everything else the same. And this will be our final equation.